All right, 11.3, talking about combinations now. Combinations. So again, back in our calculator, as we've seen 11.1 and 11.2, well, let's just clear that out. Under math, scroll over to prob. We're now going to be looking at the NCR, so number 3. We're going to be using that, okay? So let's quit that piece out. Let's jump back into our stuff. So this is our last counting technique. So we have 3 total: fundamental counting principle, which we grab from different groups like shirts, pants, shoes, earrings, or appetizer, main course, drinks, dessert. So fundamental counting principle is all about different groups. Permutations, you are grabbing from one group. You can't use anybody more than once. And the order matters, like first, second, third. President, vice president, secretary. Order of a show, whether it's a radio show, a variety show, a comedy show. Order matters. Passwords, combinations to locks. Even though it says combination lock, most of them are called combination locks. They're really not combinations. They are what we call permutation lock. Sounds weird. People are like, hey, I'm going to go buy a permutation lock. That's weird. People are like, hey, you're going to go buy a combination lock, jerkface. But no, they're really permutations, because the lock, when you're putting the numbers into a combination lock, the order matters on the numbers. It's not going to open up if you put them in any order that you want. It's a specific order, okay? So passwords and combination lock, order matters, okay? But with combinations again are like permutations. We're only going to grab from one group. So let's read up here about a combination and talk further about the differences between all 3 of these, because that's huge in here. And in your assignment, the last, like about 10 problems or so, it's going to be all up in the air, and you got to start recognizing different situations. You're going to have to recognize fundamental counting principle from a permutation, from a combination. It's going to be very, very important that you understand these differences. That's why I keep giving you lots and lots of examples of what this one is and what that one is. Okay, so a combination says that a combination of items occurs when the items are selected from the same group. So like I said a moment ago, just like in permutations, they're all selected from the same group. No item is used more than once, just like a permutation. Can't use an item more than once. But here's the difference between a permutation and a combination. The order of the items makes no difference. Okay, so this is where, like, if you go to Boston Market and you choose your sides, if I choose mashed potatoes and then the cornbread, I'm going to get mashed potatoes first, then the cornbread, because that's how I said it to them. But if I chose the cornbread and then the mashed potatoes, there's no difference there. I'm still getting my cornbread and mashed potatoes. That's a combination kind of idea. It doesn't matter how I make my order. I'm still getting the same set of sides in the end, okay? Or like when you go to Sonic, and how we were kind of talking about in the fundamental counting principle, if I get a Coke with vanilla and cherry squirted into it, I'm going to get the same drink if I did give me a Coke with vanilla then cherry squirted in it. I think I just said that. Or if I did the vanilla then the cherry. Did I do it? I can't keep things straight. Get the cherry then the vanilla. There, I think that's what I was trying to get at. So whether I do vanilla then cherry or cherry then vanilla, it's still going to be the same thing. It's cherry and vanilla in it, no matter which way I told them. Okay, that's a combination. The order does not matter. Okay, order does not matter. Permutations, the order matters. Think like, is this a first, second, third type situation? Does it matter how things work in this? Okay, in a combination, order doesn't matter. All right. So, combinations, it's got its own little formula. NCR, a combination of N things taken R at a time. The N and the R do not change from what they were from permutations. It's still the same N and R. Notice the formula is basically the permutation formula. right here, that right there is the permutation formula. All they added on was an R factorial in the bottom because the order doesn't matter. The order doesn't matter. So mashed potatoes and cornbread, and then cornbread and mashed potatoes, they're the same thing. Okay, so that's taking out all those pieces where the order didn't matter. That's why that extra R factorial is down there. Again, I can show you the formula, but you've already seen how these formulas work. I'll show it to you once. Okay, but other than that, I'm going to let the calculator do the work for us. And this is it for combinations. All we do is just basically go into problems and work this. There's no other, we don't worry about duplicates or anything like that because we don't have to worry about that. This is it. So let's take a look at a problem. All right, so it says in poker, a person is dealt 5 cards from a standard 52 card deck. The order in which the 5 cards are received does not matter. So again, there's that combination coming in here because the order doesn't matter. So it wants to know how many different card hands are possible. So your N is 52. Your R, we're going to choose or take 5. So I've got 52 C 5. So if I plug it into that formula, N factorial all over N minus R factorial, it will look like this. 52 factorial all over 52 minus 5 factorial, 5 factorial. Okay? So again, what's really going on, what it really looks like, well, before I get to that, let's do the subtraction real quick. So 52 minus 5 gives us 47 factorial, 5 factorial on the bottom. Okay? So up on top, you really have 52 times 51 times 50 times 49 times 48 times 47 times 46, 45, so on and so forth. Down on the bottom, you got the 47 times 46 times 45 times 44, so on and so forth. And then you have 5 times 4 times 3 times 2 times 1 down here as well. That's all being multiplied. But again, if we think about what happened, like in the permutation, stuff's going to cancel. All this 47 on down will cancel with the 47 down here. And so really what you're left with is these last few numbers on top, the 52, 51, 50, 49, 48. 52, 51, 50, 49, 48. And on bottom, you basically have the 5 factorial. 5 times 2, or 5 times 4. Silly me. 5 times 4 times 3 times 2 times 1. So, if you do the multiplying on that, 52 times 51 times 50 times 49 times 48 is a really, really large number, and it looks like this: 311875200. So that is 311,875,200. 5 factorial, 5 times 4 times 3 times 2 times 1. So really, we want to divide those two. Whoa, come back, number. And if you take and divide those two number, doing this on a little handheld calculator in front of me, because again, I'm kind of calculating this by hand. The final answer is 2,598,960 different 5-card hands. It's a lot. That's a lot. Again, I've just shown you everything by hand. And that's a mess, right? Let the calculator do its job. So if we go into our calculator, all we have to do is put 52C5. And it's the same way that we did with the permutations. I can type 52 in. Math, scroll over to prob, scroll down to combination. 5. There's that number I just wrote down, 2,598,960. Or, again, as I showed you a moment ago, you could just go into prob, scroll down to number 3, and then put the numbers in their little blanks as they appear. 52, 5, still the same number. Okay? So from here on out, let the calculator do its job. All right? So I have one more problem to show you with this. I call this the bear problem. Okay? And you'll hear me talk about the bear problem a lot more a little bit later on. Okay? Because they love to do this. So, in here it says a zoo has 6 male bears and 7 female bears. 2 male bears and 3 female bears will be selected for an animal exchange program with another zoo. They want to know how many 5 bear collections are possible. Okay? This is why I call this the bear problem, because it's all about bears. So, this one's a little different. And what you have to do is you have to, run a couple different things. We're actually going to use 2 counting principles to help us out. We're going to use combinations because obviously it doesn't matter which male bears we're going to pick to go. I just need 2 of them. I've got 6, just to be like you and you. Okay? It's kind of like how combinations work. If the order doesn't matter, you're just like, hey, you, and you, you're going. I don't care who it is. I just need 2 of you. Okay? Same thing with the female bears. We're just be like, I've got 7. I just need 3. So I'm like, you. Okay? If that's how you can approach a problem, when you're trying to figure out how many outcomes there are, if that's how you feel that you can answer the problem, then that's a combination for sure. If you don't care on who you're picking, I just need 3 of you. Okay, 1, 2, 3. You're good. You're in. Okay? So what's happening in this is we're going to run a combination twice because I have to run a combination. How many ways can I pick my male bears? And then I got to run a combination on how many ways can I pick my female bears? And then we use the fundamental counting principle to multiply those together and get the total. So sometimes in what I refer to as the bear problem, you're going to do a combination 2 times, and we're going to take that information and multiply it together. They love to do this kind of problem they get political in these few sections, and they love to talk about Democrats and Republicans. Okay, book loves to throw political group making at you guys in here. Okay, they also like to talk about females versus males and stuff like that too. So be ready for that. So in this one, again, we got 2 pieces we got to deal with first. We got to talk about males. Got to talk about the females. Okay? So the first thing is I got to know how many ways can I choose my males. Well, I have 6 males. Okay? And I'm choosing how many have to be shipped off. I need 2. So I need to figure that out. So I'm just going to go to my calculator. I'm going to put 6, choose 2. 6, math, choose 2. So I have 15 different ways I can select my males. Okay? Notice I'm not worried about the label yet because we're not done. Now my females, I have a total of 7 female bears, and I'm picking 3 of them to be shipped off. So, go back to our calculator. I'm just going to come up here and grab that combination I just worked with and go in and change my numbers. So I need a 7. I need a 3. So I have 35 ways to choose my females. Okay? So there's the combination part. To get to the last piece, how many ways can I make 5 bear arrangements to send off? Well, I need to take my arrangement for the males. How many ways can I do that? And then I need to pick one of those combinations from the females. And I'm going to multiply these two together. There were 15 males, or 15 ways to choose the males, 35 ways to choose the females. This is the fundamental counting principle, because I got to choose one of those combinations from the males, and I got to multiply by one of those combinations of the females. See, I'm picking from different groups. I'm picking from the males, and I'm picking from the females. That's the fundamental counting principle. So if I take that, 15 times 35, I get 525 different 5 bear combos. Horrible S. And there you go. That's how it's going to be thrown at you. You're either going to be dealing with a bear problem, or you're going to be dealing with just a regular combination type problem. Okay? So that's all there is to combinations. Now, like I said, at the end of this, they're going to throw the full gamut at you. They're just going to give you a problem and say, okay, tell me the total number of ways. This is where students get messed up. Okay? And I'm going to be right there with you, and I'm going to tell you, I even mess this up sometimes, okay? But I've gotten better at it because of the way that I'm about to talk to you about this. When you look at these problems, okay, again, look at what's going on. Are you grabbing from different groups? Like pants, shirts, shoes, appetizers, main course, drinks, desserts. If you are grabbing from more than one group, that is the fundamental counting principle. Always. If you have more than one group, fundamental counting principle. If it is one group only, then it is a permutation or combination. It is a permutation or a combination. When it comes to permutations, when you look at the group, the one group that you're dealing with, ask yourself, is it any of these type of situations? Or, is this a situation where it matters what I choose first, second, and third? Like in a radio show or a comedy show or a variety act, or like first, second, third, or like a president, vice president, secretary. If you think that situation feels like that, then it is a permutation because the order is going to matter. Okay? If it doesn't feel like a permutation situation where the order doesn't matter, okay, then that's combination. So that's how I generally look at it. First, do I have more than one group or just one group? If there's more than one, it's automatically fundamental. If there's only one group, then I ask myself, does the order matter? Is this a first, second, third type situation? If it is, permutation. If it's not, then it's a combination. Okay? So I have, on this next slide, a bunch of problems. I have 14. Okay, there they are. So I want you to pause the video, and all I want you to do is go through and figure out what this is. Because if you know what it is, then you're going to know which formula you need to run. Okay? If you know what it is, then you know which formula you need to run. Now, these are going to be straightforward problems. These aren't going to be like the ones with the bear type problem where we have more than one situation. No, these aren't that kind of problem. This is a straightforward problem here. Okay? So, excuse me. Don't think is this like a bear problem. Okay, think of about if order matters, if we have more than one group, stuff like that. Okay, pause the video, give it a shot. All right, so gone through these. On my next slide, here is the answers. So some things that I want to talk about. Don't need that page. All right. So I'm going to go back to my normal view. So for the first four, 1 was a permutation, 2 was a combination, 3 was a permutation, 4 was a combination. So I want to talk about these, just highlight some things. So in number 1, when you're talking about 8 basketball players needs a captain, co-captain. Right there, it says captain, co-captain. That's a president, vice president. That right there, automatic thing in your mind should be going off. That's a permutation. Okay, captains, co-captains, president, vice president, first, second. I'm gonna hit up 3 real quick since we're talking permutations. If you didn't know, in baseball, batting orders do matter. Okay, most of the problems that you're going to get are going to be pretty straightforward. Like you shouldn't have to know too much insight or breathe deeply into them if you've been paying attention to what I said. But in baseball, batting orders matter because usually the first person that you get up to bat is like your fastest player. He's the one that's going to get on base every time. And then in a batting order, your fourth person that goes up to bat, if you didn't know this, he's usually what we call the cleanup hitter. He's the one that should be able to kind of grand slam that ball out of the ballpark, and hopefully the first 3 people in front of you all got on base, and that now leads your team to have 4 points up on the board because that 4th batter hit a home run. Okay, so if you didn't know that is true. In baseball, batting order does matter because they're trying to have a very, very strong offense at the beginning of a game. Okay, now looking at these other ones. So if you look at 2 and 4, these are all combinations. Number 2, it says Robert and Mary are planning trips to 9 countries this year. There are 13 countries they'd like to visit. So they've got 13 countries. They're only going to choose 9. The order doesn't matter on this because it doesn't say how long they're staying anywhere. So don't assume that they're only going to go to like one place for so long and things like that unless they tell you that. So here they just want 9 countries out of 13. So they're just like you, and you. You see how that's kind of like a you situation. All they're doing is picking 9 of those 13. Doesn't matter which ones, because eventually later on, I'm sure Rob and Mary are going to go see some more. Okay, so that's definitely a combination. It doesn't matter on the order. They're going to go see 9 no matter what. Okay, and then down below it says 45 applicants for 3 computer programming positions. Again, they're all the same position. They're not different. That's not like a president, vice president, secretary situation. They're all computer programmers. You're a computer programmer, and you're a computer programmer, and you're a computer programmer. You're all the same. Just like every single one of you that are watching this, you're all students. You're a student. She's a student. He's a student. It's a student. Whatever it is, okay? You're all the same. So that's why that is a combination and not a permutation, because they're all the same position. No one is better than the other. Okay? Scrolling on down, we'll do another set of 4. Okay? So looking at number 5. This is a lot like number 2, but here's the thing in this one that makes this now a permutation. Oh, I didn't show the answers for the last 7 and 8. There we go. Here's what makes this a permutation, is because you are spending different time at these different countries. So right there, that's going to put a preference on where you want to go. Saying that, because I want to go here, I want to spend longer because this is one of the places that we want to be at the most. Okay, or maybe this place has a lot to do. So in this one, Castile and Joe planning trip 3 countries this year. There are 7 countries they'd like to visit. One trip will be 1 week long, another 2 days, and the other 2 weeks. This is permutation because of those time periods at those different places. That's like saying, like, oh, I want to go to 3 different places in Florida. I want to go to Orlando, I want to go to Tampa, and I want to go to Point Siena. Okay. Now, depending on how I do that, do I really want to spend 2 weeks in Point Siena? Heck no. Okay, what are you going to do down there? Visit Solavita every day? Okay. See what I'm saying there? There's an important, I'd probably want to do Point Siena maybe for 2 days as a rest. Okay. Maybe do a week long here in Orlando and do 2 weeks down in Tampa. Okay. So you see how there's kind of, precedence. I'm putting, I'm ranking where I'm going there. Point Siena, I only want to do 2 days because there ain't nothing. I mean, shoot, I'd probably be able to do Point Siena in 5 hours. Okay. But you get the idea. That's why the order is important on that one, because I have different lengths of windows for where I'm going to be in those countries. Number 6, you're shaking people's hands. It doesn't matter who you shake the hands with, as long as you shake everyone's hand, you're going to shake the hands with everybody. That's why that one's a combination, because it doesn't matter who I shake my hands with. I'm going to shake my hand with you. I shake my hand with you. I shake my hand with them. Okay. Doesn't matter. Okay. Number 7 says you are setting the combination on a 3-digit lock. You want to use the numbers 1, 2, 3, but don't care what order they are in. Now this one, if you said combination, I get it, because they're telling you a lot of the combination. It says the word combination. It says the order doesn't matter. But remember, this is a 3-digit lock. Numbers and their order matter on a 3-digit lock. It is a lock. It's like a password. Okay? If the order didn't matter, then crooks would be able to steal a heck of a lot more than what they do right now. Because all they have to do is just know that, oh, you use the numbers 1, 2, and 3. Doesn't matter the order I put it in, and now your lock is open. But because it is a lock, the order matters. It's a permutation. It's like a password, even though it says combination, and it doesn't matter. Okay, what doesn't matter to them? It doesn't matter that how you do those 3 numbers. But when you program those 3 numbers into the lock, that's where it matters. Okay. So number 8, again, you get that. We're talking about a race, and we're talking about the top 8 finishers. That's a permutation. Order matters. Who's getting the $1 million? Who's getting the 500? Who is getting the thanks for coming, but you didn't make it in the top? As Ricky Bobby says, if you ain't first, you're last. Ricky Bobby. Okay. All right. So 9, 10, 11. All right. And 12. We'll get to those last 2. So 17, or a team of softball players needs 3 players to go and fill the water. Doesn't matter who I pick. I just need 3 ding-dongs to go and fill the water jug. So I'll be like, you, go, fill. Yeah, it's just a combination. Okay? 5 out of 13 will ride in a car instead of a van. Does it matter who rides in the car? No, we're not setting preferences. If I'm driving, say a set of students to a conference, we have a car and a van. Does it matter who's riding with me? No, I just need 5 of you ding-dongs in the car. Okay, so again, that's why it's a combination. The order doesn't matter on 9 and 10. Now, when you look at these next ones, again, number 12, we've already talked about. It's a batting order. Order matters. Over here, number 11, we've already talked about it. President, vice president, secretary, treasurer. I'm picking who I want to be where. Okay. And then again, down here, 13 and 14, both of these are permutations. Because again, if you look at 13, it's very much like number 11. We got 4 jobs. I got a computer programmer, a software tester, a manager, a systems engineer. Order matters on that. Order matters on that, because if I'm applying for a manager type position and all of a sudden I'm a computer programmer, now I'm messed up. So now everything for the company is going to be messed up. The order matters. I should have been put into a manager position. Okay. And on number 14, again, we're talking about a race and the top 3 runners: gold, silver, bronze. See, order matters. All right, so hopefully you're starting to see the difference between a combination and a permutation. Again, when it comes to fundamental accounting principle, you have more than one group, like shirts, pants, shoes, socks, appetizer, your main meal, dessert, drinks. Fundamental accounting principle has different groups. Combination, permutation, they're all the same group. So the last thing in the assignment, that's 11.1, 11.2, 11.3, they're going to put it all together. They're going to just give you a problem and they say, okay, tell me what are the total number of different outcomes. So you got to make sure that you understand which one is which, and then all you do is run that formula. Okay. Most of them are going to be like an NPR or an NCR type situation. Okay. Majority of them. Okay. So just be careful, and I'm going to be around if you have questions. Have fun.